All right, let's finally talk about starting to get some oxygen in the atmosphere in the Proterozoic eon. So we're still in the Paleoproterozoic, just to keep that in mind. And we're going to start talking about the Great Oxidation Event, sometimes called the Great Oxidation Catastrophe, depending on who you were during the Proterozoic. And the Great Oxidation Event occurred approximately 2.4 billion years ago. So remember that during the Archean, stromatolites evolved, and what they started doing was pumping out free oxygen into the atmosphere. One of the things that we remember from the Archean is that there really was no oxygen in the atmosphere, and we know this because there's all that detrital pyrite that we find in conglomerate rocks, right? So once we start having a little bit of oxygen in the atmosphere, we start driving chemical reactions. And that's because oxygen gas will readily react with iron that is in all of our volcanic rocks, and it starts to rust the iron. So this was your last activity where you looked at this graph of the stages of the oxidation of Earth's atmosphere, where time is on the bottom here in billion years. So here we have today, and we go back about 3.8 billion years. And then on the y-axis, we have the partial pressure of oxygen gas in the atmosphere. So today we have about 21% oxygen in our atmosphere. So that's 0.2, right, because it's 20%. So 20 out of 100. So we can see that today. And then we see that there's a red line and a green line here. And the red line is the upper estimate for what oxygen content was in the atmosphere. And then the green line is the low estimate. And you can see that there's lots of times when we have pretty good understanding of what the oxygen level was in the atmosphere. And then you can see there are times we had less understanding of it. And then what these lines then tell us is a little bit about how the rate of oxygenation changed. And about 2.4 billion years ago, we have our Great Oxidation Event. And you can see that there's a very small increase in oxygen levels in the atmosphere. And then at some point, it levels out. And it levels out for like a billion years. And I was in the middle of teaching this one day, and I stopped. And I was like, this is what we see here is the rusting of iron on the Earth's surface. And then I stopped and I was like, that means for like a billion years, really the only thing that happened on Earth was a lot of rusting. That's not completely true, and we'll see a little bit more of that. But this is often referred to by geologists as the boring billion, and that's because literally the surface of the Earth rusted for a billion years. I just want you to take a minute to appreciate how crazy that is. There are certain topics in this class that when we cover, even though I've been teaching this for years, I stop and I'm like, that is nuts. I often think about that when we talk about the search for extraterrestrial intelligence. If extraterrestrial life landed on Earth at any of this time, there would be single-celled life, and the world would be rusting, and the atmosphere would be red. And wow, what a different Earth we have today. So, that's cool. Wrap your brain around that. That's kind of nuts. So what happens is that the oxidation of all the iron on the surface of the Earth creates these tremendously important economic resources that are called banded iron formations. Over 90% of the iron that we mine on Earth today is the result of the oxygenation of the Earth's atmosphere for a billion years. That's cool. So these are called banded iron formations. They're also affectionately known as BIFs. Economic geologists often call these BIFs. They are beautiful. They are these very narrowly banded iron-rich formations. There's no scale on this, which is annoying. This is in the Museum of Natural History in Manhattan. This is probably about 4 feet in length, and this is probably a little bit less than that. So banded iron formations are pretty common in the geologic record between 2 and 3 billion years ago. The iron that you see in these red bands is primarily hematite and magnetite. So if you look at the chemical formula of these, you can see that they're fairly similar, right? Hematite is the mineral that is that deep earthy red, chemical formula Fe2O3. Magnetite, as it weathers, you can definitely see a bit of that as well. That's Fe3O4. And they formed, and they're a seasonal deposit, oddly enough. They formed when iron in the seawater was uptaken and oxidized when there was oxygen in the seawater. So when there was active photosynthesis of stromatolites, the oxygen that the stromatolites got rid of as like a waste gas, that oxygen would then react with the iron, and it would cause the iron to form minerals like hematite and magnetite that would then precipitate or settle down onto the seafloor, which we're going to talk about more on the next slide. This next slide illustrates the formation process for banded iron formations. So during the summer months, when there were stromatolites releasing free oxygen into shallow water, that oxygen would react with iron in the water. Now, iron gets into the water basically by rivers flushing the continents with weathered products. And that weathering product, which is just minerals, right, gets carried down from streams and into the shallow water. So the iron would then react with the water with the oxygen in the water and form magnetite and hematite, and those would settle at the bottom. And during the summer, there would be a thick layer of iron-rich material that would be deposited. During the winter, though, there was not nearly the same concentration of photosynthesis going on from stromatolites, because we know that during winter photosynthesis slows down as the surface water gets less direct rays of the sun. So during that time period, there was a silica-rich layer that was deposited. So again, a little oxygen production in the winter in surface waters. So where does the silica come from? The silica that was in the water becomes incorporated into some of those darker layers we saw in banded iron formations, and it forms layers of chert, because silica SiO2 is the chemical formula for quartz, and chert is microcrystalline quartz. We have limestones in deeper water that are filled with chert as well, and then we also have shale that has a good amount of chert, so we call them cherty limestone and cherty shale. So the source for all this chert is actually volcanic eruptions. So volcanic eruptions are not seasonal. They go on all year long, but there's so much iron being deposited in the summer months that the silica just kind of gets mixed in with the iron-rich layer. However, in the winter, there's no iron-rich layer being deposited, so that rain of silica continues to build into these darker layers. Then, of course, seasons change, gets warm again, and during the summer months, another iron-rich layer is deposited. And so that's what we see when we look at these banded iron formations, is that the red, which is again the hematite and the magnetite, is interlayered with these darker bands that are full of silica, which is just much, much more common during winter months because you don't have photosynthesis creating any of these silica-rich layers. So all of that over time leads to important changes in the concentration of gases in the atmosphere. So one of the most important changes is that it reduces the amount of methane in the atmosphere. So just like on that graph that we looked at that had the partial pressure of oxygen in the atmosphere, here we're going to be looking at the partial pressure of another very important molecule. So CH4 is methane. And that is something that you want to put a little star in your notes. So methane is fascinating. Methane is look at that, almost looked like the word. That was really good. So methane is emitted from volcanic eruptions. It's also emitted from hydrothermal vents. But methane is really important because it is incredibly a powerful greenhouse gas. So greenhouse gases are gases in the atmosphere that trap the heat around the Earth. And in modern times, we talk a lot about carbon dioxide and how carbon dioxide is a bad greenhouse gas because it helps to trap a lot of the Earth's heat, and that leads to global warming. So methane is actually 10 times as powerful a greenhouse gas. So Greenhouse gases you can think of as like a blanket that you put on at night when it's time for bed. Sometimes you want to put on a light blanket because you want to protect yourself from monsters. Like that's me, I never sleep without a blanket. And other times, as it gets colder at night, you want more of a blanket. The blanket isn't making you warm. The blanket is helping to trap your own body heat around you. So methane is like a really thick blanket around the Earth. And so what started to happen in the atmosphere, and our atmosphere at this point was red in color because of a high concentration of methane and carbon dioxide, is that in our atmosphere, with the release of this oxygen that starts to build up in our atmosphere after the Earth is rusting, is that oxygen in the atmosphere starts to react with the methane, and it turns into water vapor, H2O, right, and carbon dioxide, CO2. So basically, the stromatolites are releasing the oxygen that turns methane into carbon dioxide. It's like taking our thick blanket and replacing it with a much lighter blanket. So that leads to a couple big changes. First of all, it leads to widespread global cooling and dramatic global cooling. And it is likely one of the contributing factors to what's called Snowball Earth much later in the Proterozoic, in the Neoproterozoic, which is the newest part of the Proterozoic. So this global cooling results in a gradual, and this is obviously our modern continental configuration, but a gradual but global cooling of the Earth, when it's predicted that and believed by a good number of scientists, to be honest, that during Snowball Earth, the entire globe was actually covered in ice. So this is a very dramatic video I'm going to show you here. And
home just feels better.
And this is what would happen.
Imagine the most profound
if there
ice
was
age you can think of. Temperatures plummet to below zero,
Snowball
even
Earth
at the
today.
equator. Before long, ice encloses our entire planet. Research suggests that this may have happened not once, but 3 times in our planet's past. Welcome to Snowball Earth.
Snowball Earth is certainly the most extreme climate change we can conceive the Earth having ever experienced.
What would happen if the world froze over today? Massive glaciers creep from the poles, crushing everything in their path.
First of all, the Canadians are going to have to dig much deeper holes when they go ice fishing. Next, the governors of Washington, Idaho, Montana, North Dakota, Minnesota, Michigan, and Maine will probably declare federal emergencies.
Cities grind to a halt. Power lines collapse and water supplies freeze. Cars won't start. Roads are cut off by ice. Buildings strain and crumble under deep drifts of snow. Everything is entombed. Our frail bodies struggle to survive.
I think human society would collapse if a Snowball Earth happened again.
The oceans freeze over. Fish die and marine ecosystems collapse. Our food supply becomes exhausted. Any surviving humans are trapped in an icy hell.
We would have a mass die-off of humans simply because we could not grow enough food under these conditions.
Incredible though it may seem, the Earth may have frozen over completely. Scientists are finding clues in unexpected places. The story begins with a mystery. In the arid Flinders Ranges in southern Australia, layers of ancient rock hold unusual stones. These stones are foreign to the area. They are known as drop stones. The drop stones are embedded in an ancient sedimentary sea floor that formed around 650 million years ago. Tim Raub, a geologist at the Californian Institute of Technology, hunts for these drop stones at the Flinders Range.
This is an example of a drop stone, a piece of ancient rock that was dropped into the ancient mud on the sea bottom.
These drop stones are visibly different from the sedimentary bedrock around them. Something powerful must have carried them here. But what? Dan Schrag, professor of Earth and Planetary Sciences at Harvard University, believes the answer is glaciers.
We actually have ice cubes here that we've made with pieces of sand and gravel in them. So these ice cubes are like the glaciers that are taking rocks from the land, and then when we put them in the water, they'll actually melt and the sand and gravel will fall to the bottom, just like the drop stones on the ocean floor.
These drop stones are evidence that at some point, this area was covered in a thick layer of ice.
With
Good
sealed
times, very
home
dramatic. All right, let's go back. So, what this really does, though, is it provides, over time, stromatolites, provide enough oxygen that there is some evolution that occurs. And Archean life is primarily organisms that we refer to today as prokaryotes. Prokaryotes, this might be a word you learned in a bio class. Prokaryotes are organisms, very, very, very simple organisms that have no nucleus and are much smaller cells. So there's no nucleus to their cell, and they're much smaller cells. In the Proterozoic eon, however, eukaryotes appeared. You are a eukaryote. Did you know that? You're a eukaryote. Eukaryotes are organisms that have cells that have a nucleus within them. They're significantly larger and they're significantly more efficient, more complex, but we have significant and regular oxygen requirements. Prokaryotes do not. Here's a couple pictures of the complexity where we compare a prokaryote and a eukaryote. So here's a prokaryote. You can see there's a cell wall and a couple different organelles, which are these smaller bits within the cell. And there's only two types of organisms today that are prokaryotes: bacteria, which certainly is tremendous diversity in bacteria, and cyanobacteria. And this is our stromatolites. Cyanobacteria are blue-green algae. So compare what a prokaryote looks like to the cell of a eukaryote. And you can see that we have a dozen organelles in our body. My daughter was just down here and she was like, ooh, endoplasmic reticulum and mitochondria. So we have a lot, right? Mitochondria, everyone knows, right, is the powerhouse of the cell. And so that's because we have oxygen and our mitochondria turns that into energy. And you can see all of the kingdoms of organisms that are eukaryotes. So eukaryotes turn out to take over the earth. Once there's oxygen in the atmosphere, we evolve the ability to live in all sorts of different places and adapt to all sorts of different ecosystems. We're incredibly efficient at it. In fact, we're way more efficient at it than stromatolites are. And so what we end up doing, eukaryotes as a collective group, is we outcompete stromatolites in almost every ecosystem in the world. So there still are stromatolites alive today, but those stromatolites only live in places that almost nothing else can live. They are restricted to what we call hypersaline environments. So here are modern stromatolites growing in the Gulf of California in Mexico. So these organisms live in hypersaline environments, meaning incredibly salty environments where almost nothing else can live. So they are in Mexico, and they're fairly common in parts of Australia that are hypersaline. But we would not be here were it not for the oxygen-making ability of stromatolites. Most kingdoms of life on Earth would not be here were it not for the stromatolites, and that's why they have to get a little bit of love in today's assignment. So the evolution of eukaryotes brings us to the end of the Paleoproterozoic and into the Mesoproterozoic, or the Middle Proterozoic, and brings us to the creation of the first supercontinent on Earth, which I'll tell you in just a sec. I don't want to leave you in suspense too long, but it's the result of a very large mountain building event called the Grenville orogeny that occurred about a little over 1 billion years ago. It is the collision of all, basically, of the cratons on Earth to form the first known supercontinent named Rodinia. So I'm going to show you a video on it that's fairly lengthy, but first I wanted to show you a map of Rodinia. And here's North America, right? So this is part of Laurentia. And all of these brown areas indicate where the Grenville orogeny occurred. It occurred not only with North America, right? But with Baltica, so this is part of Europe, with Amazonia, which is part of South America today, the Congo Craton, part of Africa, Kalahari, part of Africa, East Antarctica, obviously part of Antarctica, India, and Australia. And the yellow area here indicates some pre-existing mountain belts. So Rodinia existed for several 100 million years. And here I'm going to show you a video of the creation of Rodinia and how we see remnants of it in the state of Virginia.
I'm Callan Bentley.
So this video is hosted by Callan Bentley, who is a geologist in Northern Virginia Community College. And I think now he might be at the Charlottesville campus. But Callan does a great job of showing how we can still see remnants of Rodinia in our geology in throughout the Appalachians today.
From Northern Virginia Community College, and I want to talk to you today a little bit about the geology of the Commonwealth of Virginia. Let's start by looking at a map of Virginia. This is a geologic map of Virginia produced by Chuck Bailey from the College of William and Mary. You can see that Virginia has several different geologic provinces. There's the coastal plain over in the east, the Appalachian Plateaus over in the west, and between them we've got the Piedmont, which is the biggest physiographic province in Virginia, and we got the Valley and Ridge, and in the middle of it all is the Blue Ridge Province. And the Blue Ridge Province is actually where our story should begin. Even though it's in the middle of the state, it's actually composed of the oldest rocks in the state. So it tells sort of chapter 1 of the overall geologic history of the state. Now, Virginia records 2 complete cycles of supercontinent formation and supercontinent breakup. These cycles are often called Wilson cycles after the great Canadian geologist J. Tuzo Wilson from the University of Toronto. Wilson identified the Appalachian Mountains as being a great example of a place where the rocks recorded the evidence of supercontinents coming together, continental fragments merging with one another into a supercontinent, then breaking apart and opening up a new ocean basin. And so what I'd like to talk to you about today are the first sort of 2 stages in this diagram from Steve Marshak's textbook, Earth, the Grenville orogeny and then post-Grenville rifting of the early supercontinent that's called Rodinia. So the basic idea here is this, that supercontinents form from continental masses that merge together into a single mass, and then that lasts for a while, and then it breaks up and the fragments move apart in opposite directions. So we have evidence of continental fragments merging with one another in the basement complex of the Blue Ridge. This is a terrain that's basically dominated by plutonic igneous rocks and their metamorphosed equivalents, so meta-plutonic rocks as well. So we've got granites and we've got granite gneisses. And in general, in the Blue Ridge Basement Complex, the granite gneisses are older and the granites are younger. So the granites don't have any kind of an alignment of their grains, but the granite gneisses do have an alignment of the grains where they're lined up in planes. That's called metamorphic foliation. So basically, early packages of magma that were intruded into the crust got squeezed, and they attained this alignment of their mineral grains called a foliation, whereas the packages of magma that were intruded into the crust late in the Grenville orogeny did not have as much a chance to get squeezed, and so they don't have that foliation. Here's some looks at some of the different rocks of the basement complex. You can see they have different compositions. One of the compositions that's rather distinctive is the charnockite. It's a pyroxene-bearing granitoid. So most granitoids don't have pyroxene in them. They have amphibole instead, but this one does have this mineral pyroxene. So it's got sort of this greenish color in the fresh rock surfaces. However, you can see this one isn't completely fresh. It's got this nice, well-developed weathering rind around the exterior. Here's a look at the Old Rag Granite. This makes up Old Rag Mountain in Shenandoah National Park. It's the youngest of the Grenville-aged intrusive rocks in the basement complex. You can see its distinctive blue quartz, and it has a lack of a very well-defined foliation.
It's about 1 billion years old. Supercontinent Rodinia formed around 1 billion years ago, and then it broke up starting around 700 million years ago. You can see on this map, which is modified from a map by Paul Hoffman, that we've got Grenville age mountain belts shown in orange on many different continents, not just the east coast of North America, but wrapping all around the world in this great former supercontinent called Rodinia. So Rodinia formed, these mountain belts originated, and then time went by, the mountains were worn away, and Rodinia broke apart. One of the pieces of evidence we have for the breakup of Rodinia is some sedimentary rocks, and another piece of evidence is the extrusion of massive amounts of basalt. Basically, both of these are recorded on the edge of Virginia, here, right there on the edge of the former North American continent. But what happened at this point is ancestral continents of Africa and Europe and South America all pulled away, opening up a new ocean basin, the Iapetus Ocean, which is named for the father of Atlas in Greek mythology. So the reasoning goes something like this. The Atlantic Ocean is named for Atlas, so we named the ocean that came in the same spot as the Atlantic Ocean, but before the Atlantic Ocean, for the father of Atlas, Iapetus. Here are some of those sedimentary rocks I mentioned. This is the Swift Run Formation. It is a compositionally immature sedimentary package. You can see that it consists both of mudstone and sandstone. There's a beautiful graded bed here where we see a crisp transition from fine-grained to coarse-grained, and then a fining upwards of the sedimentary size. So a temporary increase in the energy of these sediments and a big package of sand dumped all at once. Overlying the Swift Run are various flood basalts. This is a look at a modern-day analog for the breakup of Rodinia. This is zooming into the Afar Triangle region of Ethiopia in Africa. And basically you can see here that faulting has produced a basin. Sediments are draining off of the surrounding highlands into that basin. These sediments are not traveling very far from their source to where they will ultimately be deposited. So compositionally, they are still immature. They've got lots of feldspar in them and stuff like that. Notice also the presence of lakes depositing fine-grained lake sediments, and then of course these massive outpourings of lava that become flood basalts. Okay, here's our look at flood basalts in Shenandoah National Park. These are the Catoctin Formation. What we've got here is a look at the Catoctin Formation on Catoctin Mountain in Maryland. Lots of tholeiitic flood basalts that accompanied the opening of the Iapetus Ocean. In some places they're deposited on top of the Swift Run. In other places they're deposited directly on top of the basement complex itself. So in this picture I sort of traced out there the contact between the 1100 million-year-old basement complex and the approximately 570 million-year-old Catoctin Formation. So there's about 500 million years of geologic history missing between those two rock units. The Catoctin Formation developed a lot of primary igneous structures that are typical of cooling lava flows today, like columnar jointing. Here's some examples of columnar jointing in Shenandoah National Park. Columnar jointing is also observed at places like Devil's Tower in Wyoming and the Giant's Causeway in Northern Ireland, as featured on the cover of the Led Zeppelin album Houses of the Holy. Here's an example of a basalt column that has weathered out. This is on Little Devil's Staircase Trail in Shenandoah National Park. You can see those nice angular sides to the column, how they intersect at, on average, a 120-degree angle. There's some really exquisite columns exposed on top of Compton Peak in Shenandoah National Park, about a 40-foot tall exposure. Classic columnar jointing. Also, we see things like amygdules. Amygdules are filled-in volcanic gas bubbles or vesicles, sort of a Swiss cheese style texture that develops when lava erupts and degasses, and if the bubbles don't get a chance to pop, they're preserved as void spaces in the rock. Later on, those void spaces can be filled in with mineral deposits. And we also see volcanic breccia. This is basically a fossilized lahar, a volcanic debris flow, which includes chunks of vesicular basalt in it. Stony Man Mountain showcases some of the different layers of the Catoctin Formation. So the profile of the Stony Man seen over here on the right is basically the outcrop pattern of different layers in the Catoctin Formation. The volcanic breccia we just looked at weathers away more rapidly than other rocks, so it's recessed and forms the bottom of the nose of that facial profile. The lava got to the surface through a series of conduits called feeder dikes. Feeder dikes are well expressed in Shenandoah National Park in numerous places. The orientation of the feeder dikes is strongly aligned basically from northeast towards southwest, which indicates that when the Iapetus Ocean opened up, it was opening up as ancestral Africa was pulling away in a southeasterly direction. These feeder dikes are well exposed on the trail up to the top of Old Rag Mountain, where the basalt in the dike is preferentially weathered away, and it creates these sort of staircases that hikers can walk through. Columnar jointing is also present here, not as well developed, but it forms the little steps in those staircases. So, thank you for your time, and hope you learned a little bit of information about the first two stages in the geologic